Imagine taking an infinite amount of numbers, adding them together one by one forever, and yet the final total strictly stops at a specific number, like 64. Unlike an arithmetic sequence where you move forward by adding, a geometric sequence scales through multiplication. We represent this constant multiplier with the variable r, the common ratio. To be geometric, this ratio must remain consistent between every single term. This multiplicative scaling determines how the sequence moves. Based on the size of that multiplier, the terms will either grow toward infinity or shrink toward zero. This formula shows how to find the ratio for any geometric sequence. Simply divide a term, un plus 1, by the term immediately before it, un. Take the sequence 1, -3, +9, -27. Alternating values mean a negative ratio, here -3. Now look at 32, 16, 8, and 4. When the terms are getting smaller, the common ratio is a fraction. If we divide 16 by 32, we get a ratio of +1/2. Identifying the sign and whether the ratio is a fraction tells you exactly how the sequence will behave before you start the algebra. This formula allows us to find specific future terms without calculating every step in between. un equals the first term, u1, multiplied by the ratio to the power of n minus 1. To find the 10th term of our first sequence, we substitute 1 for u1, 2 for r, and 10 for n. That gives us 1 times 2 to the power of 9, which is 512. We use n minus 1 as the exponent because the very first term hasn't been multiplied by the ratio yet. The multiplication only starts when moving to the second term. When we need to add up a specific number of terms, we use the finite sum formula, Sn. You'll see two versions in the IB formula booklet. These are mathematically the same. They are simply arranged so the denominator stays positive, depending on whether your ratio is larger or smaller than 1. Let's try it. Pause the video and calculate the sum of the first 6 terms of this sequence using the formula. Since our ratio is 1/2, we use the version with 1 minus r. We multiply the first term, 32, by 1 minus 0.5 to the 6th power, divided by 1 minus 0.5. The result is exactly 63. Using these formulas, you can pinpoint any specific term or calculate a total sum within a sequence's finite span. Return to the sequence 32, 16, 8, and 4. We know the first 6 terms sum to 63. If we add the 7th, we hit 63.5. The 8th brings us to 63.75. By the time we reach the 100th or 1,000,000th term, the numbers we are adding are so small they lose their impact on the total. They converge on the 64 ceiling but never cross it. We can calculate this limit using the infinite sum formula, u sub 1 divided by 1 minus r. Plugging in 32 over 1 minus 1/2 proves that an infinite amount of these terms totals exactly 64. This formula only works if the terms are shrinking. This means the absolute value of r must be less than 1, placing r between -1 and +1. You can take a screenshot of these 3 formulas. You will need all of them for your exam. When a common ratio stays between -1 and +1, future terms become insignificant, allowing an infinite series to reach a finite destination.